You know how you try to guess what's happening somewhere you can't see just based on a few little clues? We do it all the time, right? Trying to figure out a friend's mood just from a text, or what the traffic's going to be like up ahead just from the sound of sirens. Well, today, we're going to crack the code on a seriously powerful tool designed to do exactly that, uncovering hidden patterns from the stuff we can actually see.
Okay, so to really get how this works, let's start with a simple puzzle. It's a classic little thought experiment about a friend named Bob, and it perfectly sets up the challenge of trying to see the unseen. So picture this. Your friend Bob lives way out of town. You chat on the phone every day, but you have absolutely no idea if it's sunny or rainy where he is. But he does tell you one of three things he did that day. He went for a walk, he went shopping, or he stayed inside to clean. Now your job, your challenge, is to use only that information, his activities, to figure out the most likely sequence of weather over the last few days.
Now, I know it sounds like a simple guessing game, doesn't it? But this exact setup, using a series of things you can see to figure out a series of things you can't, is the absolute foundation for some incredibly sophisticated technology. This little puzzle, this is our way in.
So how do we solve this mystery? Well, we need a special kind of detective, a statistical detective. So let's meet our tool for the job, the Hidden Markov Model, or HMM for short.
When you boil it all down, that's really all an HMM is. It's a system that's built to handle two layers of information. First, you've got a hidden process, something we really care about but can't see directly, like the weather. And then second, you have the observations, the data we can see that's being influenced by that hidden stuff, like Bob's activities. The HMM is basically the mathematical engine that builds a bridge between the two. And this right here shows that relationship perfectly. The top row, that's the hidden stuff we want to know, the weather. The bottom row, that's what we do know, what Bob's been up to. The model's whole job is to figure out how that top row caused the bottom row. Okay, but for an HMM to work its magic, it can't just guess blindly. It needs some inside information. It needs to know the rules of Bob's world. And in statistics, rules is just a fancy word for probabilities. It needs to know the chances of certain things happening. The model relies on two key types of clues. First up, we have transition probabilities. This is all about the hidden state itself. Pretty simple. If you know it's rainy today, what's the chance it'll be sunny tomorrow? Then we have emission probabilities. This is the link between the hidden and the visible. So if we know it's a sunny day, what's the chance Bob emits the observation went for a walk? This whole chart maps out the entire system for us. Those big circles up top, rainy and sunny, those are our hidden states. The circles at the bottom are the things we can observe. See the solid arrows between the weather states? Those are the transition probabilities, the chance of the weather changing. And the dotted arrows pointing down show the emission probabilities, the chance Bob does something because of the weather. Now this chart shows us something really important about the transitions. Notice how high the chances are that the weather stays the same. A 70% chance a rainy day is followed by another rainy day, and a 60% chance for sunny. That tells our model that the weather in Bob's world has some inertia. It doesn't just flip a coin every single day. And this is a perfect illustration of those emission probabilities. If it's sunny, Bob is super likely to go for a walk, a 60% chance. But on the flip side, if Bob told you he was cleaning, you'd be pretty suspicious it was a rainy day, right? Because the chance of him cleaning when it's sunny is only 10%. His actions are a really powerful clue. Okay, so we have our hidden states, our observations, and all the probabilities that connect them. Now for the main event. How does the model actually take what Bob did and work backward to figure out the most likely weather? And here is the key. We're not just guessing the weather for one single day. We are trying to find the most likely path over time. If Bob tells you he walked, then shopped, then walked again, we need the entire sequence of weather, like sunny, rainy, sunny, that best explains that whole pattern. This is where a clever bit of math comes in. The most famous algorithm for this is called the Viterbi algorithm. You can think of it like this. It maps out every single possible weather sequence that could have happened. Then, using all those probabilities we gave it, it calculates a final score for each path. And in the end, it just picks the one with the highest score, the single strongest path through all the possibilities. And that path, that's our answer. And here's the big reveal, the aha moment. This really elegant logic we've been using for Bob's weather isn't just for fun little puzzles. It is the fundamental engine behind some of the most impressive technology we use every single day. Yeah, the goal is always the same. You want to recover a sequence of data you can't see by using the data that you can. And that one simple, powerful idea, It unlocks a staggering number of applications.
Think about speech recognition, Siri or your Google Assistant. The sound waves hitting your phone's microphone, those are the observations. The actual words you were trying to say, those are the hidden states. The HMM finds the most likely sequence of words that could have made that sound. It's the exact same logic.
This same idea is an absolute game changer in bioinformatics. Scientists can see a long string of DNA bases, A, C, G, and T. That's what they observe, but the hidden state they're looking for is whether some part of that string is a gene or not. HMMs are a cornerstone of how we find genes today.
And the list just keeps going. In finance, stock prices are the observations, while the hidden market state, like volatile or stable, is what everyone wants to know. Your smartwatch uses sensor data as observations to guess your hidden activity. Are you walking, running, or sleeping? And really, that's the big takeaway here. The very same statistical detective we used for our simple weather game is what allows your phone to translate your speech into text. A hidden sequence of weather, a hidden sequence of words. To the Hidden Markov Model, it's all just a path waiting to be found.
Kind of makes you wonder, doesn't it? What else is out there? When you look at all the clues in the world around you, what hidden processes are actually driving them? What unseen codes are just waiting for the right tool to bring them into the light?